checking out the videos for this class. I'm kind of assuming not since you're actually here, so. I'll try to talk to Susan downstairs about picking up a microphone for me because with the camera sitting there, the audio just is not coming through as clear as I would like it. Also, I'm going to try to make sure that I don't rush at the end of the hour like I did on Thursday. After reviewing it, it was very obvious that I didn't really provide any good description of what was going on with the rotation matrices. We'll go back over them today and I'll actually show you a little more what's going on when we're hitting or using those rotation matrices to go through and perform a rotation transformation. Also keep in mind that the assignment, first homework assignment is due today. I have received it from virtually everyone, but there are several students that haven't submitted it yet, so please make sure you get it turned in for me. If I have received it, I have graded it, and your grade is sitting there. The big thing that, or the question that a few people missed, well, I'll discuss that tomorrow, I guess, otherwise I will be giving it away for those of you that haven't turned it in. Okay, so today we're going to go through and review translation transformations just in the warm-up. Then we're going to go through and review these rotation transformations. Then we're going to introduce compound transformations. And finally, introduce the X, Y, Z fixed angle transformation. This is also commonly known as your pitch, yaw, and roll transformation. So we'll be able to associate this with the 3-axis of motion on an airplane if you're interested in such things. For our warm-up, find the transformation from or to C from frame A if the transformation to B from frame A has a position vector of 4, 2, and 3, and then the transformation from frame B to frame C has a position vector of 2, -4, 2. And I'll give you just a minute or two to do that. Okay, so how much time do you really need to do this?
We're just adding those together?
Yeah, ultimately, when we're looking at these translation transformations, it's nothing more than adding the displacements together. We could say that we have a position vector that's defined in A that points to the origin of B, and then we have a position vector that defines the origin of C in terms of B. So in this case, we could say, well, the position vector pointing at the origin of B is right here. It is the 4, 2, and 3. Oops. And the position vector pointing at C from B is the 2, -4, and 2. And therefore, the position vector in terms of A that points to the origin of C is going to equal 4 plus 2 is 6. 2 plus -4 is -2. And 3 plus 2 is 5. Okay, and yep, that's okay. Now, if we were to go through and actually define this using our matrix multiplication, we would know that, I'm about to run out of room here, we would know that the transformation from A to C is equal to the transformation from A to B times the transformation from B to C. So we would have this first matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm filling in the first three columns first just because it's easy. Oops. That's 2, 3, 1. And then we have the second transformation, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 2, -4, 2, and 1. And we see when we go through and perform these matrix multiplications, we have 2 plus 0 plus 0 plus 4 to give us 6. I'll fill in the first several columns. If you want to confirm that the first three columns turn out to be 1, 0, 0, 0, 1, 0, and so on and so forth, feel free to do the multiplication by hand, but this is just to demonstrate that we end up with the exact same result. The second row by the last column would give us 0, -4, plus 0, plus 2 to give us a -2. And finally we have a 0 plus a 0 plus a 2 plus a 3 to give us 5. And finally 0 plus 0 plus a 0 plus 1 to give us a 1. And right there is the same displacement vector that we saw by taking the origin displacement vectors that we saw. That makes sense? Okay, so I'll buzz through and show you how to review doing this in MATLAB real quick, and then this will lead us on into the next section, which is providing a representation for our, let me zoom out, rotate it just a little bit. Now it's okay. So if you have not used MATLAB before, we're going to be doing virtually everything in this class within scripts. So we can open a new script, and in this case, a lot of what we are going to do is going to be the same as what we did before. So I'm going to go through and say that I'm holding the image on so that it does not clear the image between different screenshots or between different plots. I'm going to turn on the grid just to make sure that I have a reference that I can use. I'm going to define our axis, and this is going to be subjective in nature. One thing that we'll be able to do later on is define the minimum and maximum quantities in our array and use those to define the minimum max range on our axis. But for now, I'm just going to assign it statically. Okay, now in MATLAB, just for those of you that are interested in such things, the semicolon is not required to end a line. What the semicolon does is it prevents verbose from occurring at the end of that line. So what verbose is if a instruction has some kind of output, the semicolon will suppress that output. Okay? In the case of a math operator involving large matrices, typically you want to suppress that output, otherwise you're just going to end up with a bunch of rolling data. Okay. I, out of habit, include a semicolon at the end of each line, but in in the cases of these first three statements, it's simply not necessary. So I'm then going to find my view kind of arbitrarily, and you'll see in a second that we can move it around if we want. So this is just going to be a point in space that I'm viewing the plot from. And then I'm going to go through and define my frames. Now I'm going to do the same thing as I did before. I'm going to define the I, J, and K vectors so that we can plot it using the plot 3 commands. But in this case, I'm going to call it frame A, just so that it's a little more apparent to me. And if you recall, I went through and defined this, listing all of the possible X portions in the first row. So this is the origin of the first segment, the end of the first segment, origin end of the second segment, and the third segment respectively. One thing that's kind of a good idea, if you need it, is to, when you're entering in matrix information, do each row on a separate row. That way it's easier for you to interpret the matrices. So the second row corresponds with the X or the Y information. The third row corresponds with the Z information. And then the fourth row is just to maintain dimensionality in our matrix. So this is the data for our I, J, and K vectors in our frame A. That makes sense? And just for the practice, I'll let you guys type along. In fact, this is at the heart of next week's assignment, which is already posted for you. You will be have the option to use MATLAB on several of the assignments that or problems on the upcoming assignment, just to give you a visualization of what's going on. So that makes sense. Let me do the mag just so you can. That better? Okay, and then I'm going to go through and define my transformations. So I'm going to define the first transformation as defining frame B and frame A. And then this will be, let's see, it's 1, 0, 0, 4, 0, 1, 0, 2, and this is straight off the problem on the board. 3, and then 0, 0, 0, 1. Makes sense? Now this is a good example. If I had not included the semicolon at the end of either of these statements, then it would echo this out to the instruction window or command window, which typically is not what we want to do. Okay, the transformation of C in B will equal 1, 0, 0, and C2, 0, 1, 0, -4, 0, 0, 1, 2, and 0, 0, 0. Okay, now there's a couple things here. Let me first make sure that this is showing up on the camera real quick. Yep, looking good. Okay, there's a couple things here. First off, when you're defining matrix data as we have here, you can either use a space or a comma to separate the cells, okay, or the elements within that matrix. So I could have either put 0 space 1 space or 0, comma, 1, comma, 0. Either way will get the job done. Note that the commas or the spaces separate row elements, and then the semicolons separate column elements. Okay, so pay close attention to that. But now we have our two transformations and our frame data defined. And there we go. Okay, so now what I can do is I can go through and say that frame B is going to equal the transformation from or of B expressed in A, that is transformation of frame B expressed in frame A, and this is going to equal, let's see, no, this is going to be multiplied by the data expressed in frame A. Again, we used semicolon to suppress the output. Frame C will equal, let's see, how should we do this? Is it going to be B expressed in A times C expressed in B, or vice versa? Well, we can take a look at this both ways, but I'm going to tell you that it's going to be B expressed in A times transformation of C expressed in B times frame A. Okay, and let me make sure I did that right. Yes, I did. Okay. And what we have to think about here, and this isn't necessarily so important to us when we're looking at translations, and you'll understand more why I say that hopefully here in a few minutes. But when we get to rotations, this becomes extremely important, because ultimately the order that you apply these transformations determines what operation occurs first. Do you rotate and then translate, or do you translate and then rotate? Two entirely different things, isn't it? So if we were to have a rotation matrix or a rotation transformation here followed by a translation, we'd be pointing in a direction and then moving along that vector. Whereas if we had a translation occurring first followed by a rotation, we'd be moving along a vector and then rotating to orientate our frame. That makes sense? So the order in which we apply these transformations is extremely important to us. Did you have a question or just, okay. Okay, so at this point we can just go to town on plotting our data, and what you can see is that our data is going to come from the rows of frame A, B, and C. So we can plot 3D frame A. Let's see, the first row, all of the information. Let's see, frame A, the second row, and all of the information. And then finally, frame A, the third row, and all the information. Now, what does that mean? We've talked about this plot 3 instruction before, but let's review what this is actually doing for us. Keep in mind that this first vector here, this is a row vector in frame A. This is specifying the X information, the Y information, and the Z information. And since we formatted that matrix associated with frame A in an X row, Y row, and Z row format, by pulling out that row data, we're providing the information for the X, Y, and Z components of this plot. Okay, and I'm going to specify that this is black. And, let's see, with that, and I'll go ahead and do a slightly darker line width. There are a couple instructions that I do or a couple options I do all the time. For example, well, let me do this. Okay, so a couple of things I do all the time is I try to always specify the color, and then I try to always increase the line width, because the default line width is 1, and that is oftentimes kind of hard to see, particularly in a 3D plot. So our second plot instruction is going to look incredibly similar, so I'm just going to copy that one. And change it to frame B. And I'll put this one in blue. And same thing again. Next plot's going to look very similar. So I'm going to pull the data out of frame C and put this one in red. The stuff inside the quotes is not case sensitive, so you can make it uppercase, lowercase, whatever you want. It doesn't really matter. So let's go ahead and run this just to see what we have. So we can see that in this case we have frame A sitting here at the origin. We have frame B sitting over here in space, and finally frame C. Now, much like I did previously, I'm going to draw my translation vectors in here in just a second so that I can actually see where the translation is taking place. That makes sense. This I, J, and K is what was packaged in your frame A matrix. We're just moving that frame A around to the different positions. That makes sense? Did you, are you having problems?
Yeah, it says assignment 2, undefined function assignment for input arguments of type char. So just
So,
named assignment 2.
more than likely. Let's see. This way. Yeah.
I just had a misspelled word. My
Yeah.
frame was misspelled.
I'm sure that's what it is, I'm just not seeing it here. Here. Can you see that, Lance? Generally, we use a real number.
Good. Sore. We'll not be able to do the whole running thing. Doesn't agree with me.
Yeah, I don't know. I can check.
Oh, yeah, it's, it says you put a space in here.
Oh, okay. This is
So,
sure.
yeah, oh, okay. So one thing you want to make sure that you don't do on that line is put spaces in file names. Always use either underscores or no space. So in this case, yeah, just get rid of that and now run it. Because then what it'll do is it'll take the numeric value as a parameter passed into that function, and that causes you a problem. Okay, so another thing that you can do is go through and put in your translation vectors just for the heck of it. And this again is going to be a plot 3. And I'm just going to say that my first vector is going to be going from frame A. Let's see, so it'll be 1, 1 to frame B. Let's see, is that
Are you supposed to put frame A for the first one, or just frame 1, 1?
yeah. Okay. Of course, I need to make sure that I indicate that it is frame A. Oh, did you guys see Transformers?
Not yet.
No comment. Okay, so we're going to go second row, first column, and frame B, second row, first column. And we can actually do the same thing here. Now, one of the errors that I have run into in the past is only putting 2 dots instead of 3. That will lead you to a very difficult problem to spot. So be careful doing so. A 3, 1 to frame B 3, 1. And much like before, I'll specify this in green and line width. So that will plot the translation vector from A to B, and then to get from B to C, it will just update my same statement. I do a lot of copying and pasting if you don't notice. And with that then, we can run it, and sure enough, we have our translation vectors. That makes sense.
Can you go back down to your code?
Sure.
There you go. I just need to do that.
Oh,
last
just
part.
choose B.
Now, the other thing you can do is you can actually include the legend, which is really handy here. The legend will color code the coloring options that you have selected. So let me demonstrate this. So the first one will be associated with the first color you selected for your palette. The second will be associated with the second color you chose for your palette. The third for your third color. And in this case, I don't want to necessarily do anything with my fourth. Now, one of the more interesting features in MATLAB is if you leave a plot open, it will not come to the forefront when you run your script again. So I always always prefer to close the plot, that way I know that it's updated and it comes to the front. And now we have our 3 frames color coded appropriately. Good. Okay, now we can actually take quite a bit out of this. Let me go and run up the screen here and pause that. And actually, I'm going to do this kind of in a different order here, but we can take some really important information out of this. Before I go on, was there any questions on that? That's already included in the notes for today, so you'll have it available to compare with your sample when you go through it or review the notes online. So in this case, we had, let's see, we had the transformation defined in A for C, and we said that that was equal to the transformation from A to B times the transformation from B to C. What if we wanted to find the transformation from A to B, and we knew these other two transformations?
Divide.
Not divide.
Is it plus or minus each other?
Well, if you're looking at the position vectors themselves, yeah, it'd absolutely be just subtracting off the vector and being done with it.
Yeah.
But how are we going to go through and isolate this term here?
Multiplication by that inverse.
Oh, very good. We have to get rid of this final term, right? So we can go through and hit both sides with the inverse of the transformation from B to C. So we would have A to C times the inverse from B to C, and that will equal the transformation from B, or from A to B. Now, what could we go through and interpret this, the inverse of the transformation from B to C as?
Vector headed in the opposite direction of the
Exactly.
original one.
So this is the vector heading the opposite direction, so we could assume that this inverse is the same as the transformation relating B in terms of C. And when we do so, we see that, once again, that idea of the subscripts doing the work for us actually works out. Because in this case, the C cancels the C, leaving us with the transformation from A, or from B, no, I'm sorry, the transformation of B expressed in A, which is what we were after. That makes sense? So this is at the heart of, or this is an example of one of the homework problems on the upcoming assignment. If we were given the transformation, so the transformation from A to B, and it was it should be zeros, 0, 0, 0, and then 1, 2, 3, 1. And we define the transformation from A to C as three, 4, 5. Then we could go through and say that the transformation from B to C is equal to, well, you guys tell me. So it would be the transformation from A to C times the transformation, well, you know, maybe, nah, I think I can do this, so. So it's going to be the transformation to A to C times the inverse of the transformation from A to B. That makes sense. And we know that this will be just the vector pointing in the other direction. So it'll be -1, -2, -3. We saw that last week when we went through and reviewed this. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1, and 3, 4, 5 times 1, 0, 0, negative 1, 0, 1, 0, negative 2, 0, 0, 1, negative 3, and 0, 0, 0, 1. Keep in mind that we don't necessarily have to remember this trait, that the inverse of A to B is just A to B with negative signs in there. MATLAB will do this for us, right? It's just one of those things that kind of help us keep the geometry, stay mindful of the geometry and what's going on here. Yeah.
Would be a negative 1 in the bottom right, or does that just stay?
No, it will stay a 1 because only your position vector is pointing in the other direction. We're not doing anything at all with this final row vector here. Okay, so in this case, we would have C expressed in B, or translation from B to C, would equal 1, 0, 0. 3 minus 1 is 2, 0, 1, 0. 4 minus 2 is 2, 0, 0, 1. 5 minus 3 is surprisingly easy to calculate, 0, 0, 0, 1. So, what does this allow us to do then? Now this doesn't happen too often, but let's say that we knew all of the information about the joints in our robot with the exception of one, okay? We knew the position of the end effector, we knew all the characteristics of the robot, but we were missing some of the parameters for one segment or one joint. This would allow us to go through and use those forward kinematics to solve for that unknown parameter, okay? Again, that's not something that's very common. In fact, I can't think of a situation where it would really occur. But the fact is, if we did lose information about a joint or a wing, we could go through and figure it out. Okay, so with that then, does this make sense?
Yeah, it just seems like almost like we're cheating with the inverse. Like we have a bunch of information that we know about it, so we can make this really simple.
Well, and that's the thing. I mean, everything we're going to do in robotics, we're going to try to make these matrices as simple as possible because we don't want these overly complex. When we get to this XYZ fixed angle transformation, that's great, it's really cool, but we're not going to use it, okay? Because we're going to never have a joint with 3 degrees of freedom associated with it. Every joint that we analyze is going to have a single degree of freedom associated with it. Therefore, we're going to be considering an X transformation, a Y transformation, or a Z transformation. If we need to put those together to provide additional degrees of freedom, we're going to consider these individually to get the job done.
But since we know where all the joints are and the way they're related, we don't ever run into situations where we try to calculate an inverse and it's like, does not exist, or...
Sometimes you do.
Okay.
So what's an example where we would end up with a inverse kinematic solution that does not exist?
I can't remember exactly. We can't solve like the...
So the example they gave in the textbook was the situation of the gunners that were sitting in the B-29s back in World War II. What they'd have is 2 degrees of freedom. They'd have a elevation and then a rotation. So what would happen is that when they rotated straight up, in order to continue tracking the object, well, they couldn't pitch any further back because they were restricted to a maximum 90-degree angle. So they'd have to instantaneously rotate 180 degrees to continue tracking that target down. So that's what's known as a singularity within the solution, because momentarily you're unable to produce a solution because ultimately you need to provide a very quick translation or rotation of some sort in order to continue the motion that you're desiring. So this happens when you have two axes that are aligned at a particular configuration. So if you have, say, frame A and frame B that are just happening to point in the same direction at an instant, then ultimately you can have infinite number of solutions associated with that particular configuration. Now, it's not uncommon, particularly in inverse kinematics, to run into situations where you have multiple solutions, but you never want to have infinite solutions. That becomes a nightmare, because then you can rotate your wrist any number of different positions in order to achieve that solution.
And is that when we add, I have to review my notes from linear algebra, is that when we'd add a parameter? We parameterize these things?
Exactly.
Okay.
When we're defining our robot, we want to have redundancy, and those singularities are a result of the redundancy in our robot, but it's something that we want to have in order to allow us to avoid obstacles. So for example, if we wanted to position the angle factor here or here, well, without that obstacle, we wouldn't need all 6 degrees of freedom. But with this obstacle, in order to position the end effector in an appropriate orientation, we have to have that extra degree of freedom in order to allow us to achieve that position and orientation. That makes sense? Okay, so with that then, let's go through and review our rotation transformations, and we'll take a look at how we can work with these in MATLAB real quick, and then we'll move on hopefully to our X, Y, and Z transformation, just because it's kind of cool. Again, it's something that we don't necessarily run into in robotics, simply because we try to restrict each joint to having exactly 1 degree of freedom associated with it, but it's something that we'll talk about because it's kind of part of the sequencing of the material. So, okay, so when we went through and defined a rotation about Z, what did that look like?
Is the cosine of alpha
Good.
in sines?
Now, I'm going to make sure that I'm doing this properly, just to make sure that our angles are properly named. So we say that the rotation about the z-axis is dependent on alpha, so we got that right. And then the 3x3 rotation matrix, which we can reconfigure into a homogeneous transformation format, will equal the cosine of alpha, go ahead,
Negative sine.
negative sine of alpha and 0, and then a sine of alpha, cosine of alpha, 0. And since the z-axis is the one that we're rotating about, we don't want to manipulate the z-axis. Therefore, we leave the z vector, either the row or the column vector alone.
Is that first one a negative cosine?
No, it's a positive cosine, negative sine, 0, and then sine, cosine, 0, and then 0, 0, 1. Okay, so I was just thinking about something. Keep in mind that if you want to implement this in MATLAB, we'll see this again here in a minute or so. If you just implement the sine and cosine functions in MATLAB, those are the radian dependent functions. So if you use just sine and cosine, you had better be making sure that you express alpha in radians. Now, since we're engineers and not mathematicians, more likely everything we're going to want to do is in degrees. Therefore, we're going to use the cosine d and then sine d. So cos d and sin d to calculate the cosine of a degree measurement and the sine of a degree measurement. And again, that's in the example in the notes for you. So, okay, what about the rotation about y?
Don't we have the zeros kind of in that cross pattern?
Here. Yeah, in this case, we've got the cross pattern going on because it's y that is being manipulated. So we want to leave y alone and adjust the x and z components. So in this case, if we start in the lower lower right-hand corner, we know that that is our cosine of beta. And beta corresponds with the angle definition that you're using for a y, or a rotation about y. Okay, and then wrapping this on around, it is a negative sine of beta, sine of beta, and cosine of beta. Okay, and how about the rotation about x then? Last week when I did this, I went through and just used theta, I think, all the way across, but I'm using this so that we can associate each of these with our pitch, yaw, and roll angles, which is ultimately what we want to do.
Is it the bottom right for,
Say again.
the bottom right for?
It is the bottom right for, so when we're going through and doing a rotation about x, we're going to say that this is gamma. So we're going to say that x is unaffected, and we have a rotation about gamma here, so that's cosine of gamma, negative sine of gamma, sine of gamma, and cosine of gamma. Okay, so what do you suppose each of these look like? Okay, so a rotation about z, what's this going to look like?
Just twisting it around.
Yeah, we can use that same right-hand rule that we did before. Point our thumb in the direction of the positive axis that we're rotating about, and our fingers represent the positive rotation as the angle is increasing. So in this case, if we move our, or point our thumb in the positive z, we're rotating around z in a positive direction. Therefore, if we have an alpha here, this would be alpha degrees, this would be alpha degrees, and our z would remain the same. In fact, since we know that even in a rotated frame, we are still dealing with an orthonormal set, we'd only really have to specify alpha once, wouldn't we? Because we know that this is orthonormal, therefore, if this is our x, y is perpendicular, and z is still perpendicular. Good. How about our rotation about y then? Who wants to come up and draw line? Let me do this. Who wants to come up and draw a rotation about y? Okay, so using the right-hand rule again, we point in the positive y direction, and we see that the rotation is going to occur in a clockwise direction, or, I'm sorry, as our hands roll about that axis. So that means, let's see, we're going to have X, Z, this will be our positive X, and our angle beta will occur right here. Okay, and then of course we're leaving Z unaffected. Unaffected.
You mean Y?
Y unaffected, yes, sorry. And finally, a rotation about X is going to look very similar. Our rotation about X, and I'll draw it right here, we'll have our frame X, Y, and Z hanging out here, and if we're rotating about X, then we will have our right hand rule pointing in the positive direction, rotating around. So here will be our gamma, this will be our new Y, our new Z, and we're rotating about X. Good? And let me make sure I get this right. Let's see, we have rotation about Z is referred to as yaw. Rotation about Y is referred to as pitch. And rotation about X is referred to as roll. What does this imply about, and by the way, if any of you are interested in how this really applies to aviation, Dr. Johnson has his pilot's license, so he can fill you in on all of the details. But how does this, what does this suggest about aviation and how the coordinate system is laid out in the plane?
Yaw would be like your left and right movement. Pitch
Okay.
would be like, well, or it would be up and down. Pitch is like left and right, and roll is from side to side.
Side to side. Okay, so if we go through and look at the plane, our coordinate system, so let me see if I can do this. So we've got something like that. Where's our x-axis?
Like straight across the center.
Straight across center is through the fuselage. In fact, our positive x is pointing in the direction the plane's going. Okay. What about our y-axis?
Going straight up. Or isn't it like straight up and down from that?
The y-axis is across the wings. Okay. So the y-axis is the axis that the wings lay in. So this is our y-axis, and then our z-axis is up and down. Now, interesting, which direction is our positive z? I thought this was really interesting this morning when I saw this.
I'm guessing at the bottom.
Yeah, it's the direction that ground is facing. So, in this case, this is our positive z, and so if we were to go through and specify our positive x, we'd go through and wrap around like this, so, or our positive z, wrapping around like this, we would see that, let's see, how does that work?
It'd be your like left and right movements.
So this would be positive y, is that correct?
It doesn't really matter, I think, on this one.
Well, if we just follow that same right-hand rule that we did before, this would be your positive y, okay? But you're right, it doesn't really matter. It just is kind of an arbitrary definition here. So when we go through and roll the play, we're rolling about, let's see, about,
Is it x-axis?
yeah, about x-axis. So
Does
sure
roll
enough, we're
plane
tilting
just-
that plane side to side and rolling the fuselage. when we're pitching about the y-axis, so we're moving the nose up and down. And finally, the yaw is the left and right turn, which would be achieved with tail rudder, so. Cool. Okay, so how would we go through and develop a transformation that represents all three of these motions? And before we do so, let's just take a look at how this would be interpreted on MATLAB. Really, we don't have to go through and do a whole lot of modification here. I'm going to go through and remark out the second line. This guy. Okay, so what angle do you want to rotate about? And which axis do you want to rotate about? Let's do something relatively easy to interpret, like maybe a 30-degree angle or 45-degree angle. And I will say that I'm rotating about the z-axis, just to demonstrate this initially. So I'm going to say that there's no offset, meaning that frame B is has the same origin as frame A, and in this case I'm rotating about z, so I will have, about z. So I will have cosine D of 45 degrees, sine D of 45 degrees, and that should be negative, shouldn't it? Sine D of 45 degrees and cosine D of 45 degrees. So when we go through and run this, what we see, let me make sure I have everything.
Would you use the commented out?
Just so that it wouldn't try to produce the second and third plots. This is the same code segment that I used from our warm-up example. So I'm just deleting the stuff or removing the parts that I don't need. I'm leaving them in here because here in a second when we go through and look at our compound transformations, we'll be putting them back in, so.
I think it's the percent.
Okay.
Oh, the question was how you comment out?
Yeah.
Sorry. Yeah, you just use the percent symbol, so. Okay. So in this case, also I need to change our view window, otherwise we're going to be really small. Maybe our view, oh, I did delete the. Okay, so as we intended this as a rotation about z, so of course the z vector stays the same, and our x vector translates around the z-axis by 45 degrees, as does our y-axis, okay? If we want to go through and do the same thing with our y-axis, if we want to do a rotation about y, we can do so.